Hi guys, this is Dr. Cotto. Sorry about that. I should have paused the video, but I accidentally stopped it. So I'm going to pick up where I left off. This is video number 2 for chapter 14, which is chemical kinetics. And we were talking about what do you want to follow when you are looking at the rate of a chemical reaction, how fast the chemical reaction occurs. And we said you can either watch the disappearance of any of the reactants. Here's the 2 reactants. Or you could follow the formation of the product, okay? So I start out, right? What does this in brackets mean? Moles per liter of either substance A, B, or C. So if I had the same exact time scale here and I had 3 meters and I was watching the chemical reaction, these 2 guys would disappear and this one would grow in, okay? And again, we're always versus time, okay? So there is always this kind of petering out effect, right? Where it starts off with a huge slope, but the slope drops off. Here it starts off with a huge positive slope, but the slope drops off. Well, the reason why that's happening is the concentration of the reactants is being used up. Well, if there's less of them around as the reaction is going on in time, you're not replenishing them by like dumping them in at the same time that they're reacting, then the reaction naturally has to slow down. Because how are molecules of A and B going to find one another in the solution if their concentration is dropping? Okay, trying to think of a good analogy for that. Okay, here's a good analogy for that. The chemical reaction is watching all of the people leave the stadium, right? So at the moment the baseball game is over and everyone is going to leave the stadium, the likelihood of people bumping into each other, which is chemical reactions, is going to be very high because their concentration of the reactants, the people leaving the stadium, is very high. So the likelihood that you're going to bump into the person next to you is very high. But over time, as the people exit the stadium, there's less and less people in the stadium. So the last few people who leave the stadium have it very easy. There's very hard for them to bump into each other. They're probably just going to walk right past one another and even be in totally different exits, right? Where in the beginning, they are stuck right on top of one another. There's so many of them, okay? If you're watching the product, here's people making it to their cars. In the beginning, a lot of them are going to make it to their cars right away, and then it's going to tail off because they're all already home, the majority of them. So that's what's going to happen with time, okay? All right. We can study either the instantaneous rate of the chemical reaction, which is what I was sort of showing you there, or we could study the average rate. So the average rate is pick 2 points in time and measure the concentration of whatever it is you're interested in. In this case, we'll go back to X, right? The moles per liter of X with time. So all I have to do, if I want to do that, is I go and I look at my graph. Instead of making this C, let's make this X. Right? And anytime we do a delta, we do a change, I want the change in X, I need X2. I need the X that's further along in time, right? Now, if I'm watching this, this is a product grow in, so this number is going to be higher. So at that time, T2, I have a concentration X2, okay? And I want to know what is the average rate from that time to this other time that's earlier? The initial time could be 0. It's going to be whatever is in the question, okay? This would be T1 earlier in the situation. And what's its concentration? Whatever the value of X would be this way, that would be X1. So both X1 and T1 are smaller numbers than X2 and T2. So my change, my delta T, my delta X over delta T is the change in the X. So I need X2 minus X1, all divided by T2 minus T1. So it's the average over those 2 points, over that interval. So how would I draw that? Well, let me get a ruler and draw that for you. So the average is just going to be the straight line difference, and I just take the slope of that line. Okay? So that would be how I would measure the average rate. Okay, and I chose to measure the change in x over time. Make this a little bigger. Okay. Well, if I wanted the instantaneous rate at any point as this guy is going up, I take the tangent to the line exactly at that point. See, this slope of the line is always changing. Here, it's going to be less as I get further up. In the beginning, look at that slope of the line is going to be the greatest. So the instantaneous rate is changing, okay, at any given point. So I'll try to draw that for you one more time. If I asked you, here it is. What is the instantaneous rate at t? We'll call it T2 at this point right there. So you go up to that point and you need the slope of the line that's totally parallel to the line right at that point. So the instantaneous rate at that point, I could measure by looking at the slope of the line that's tangent at that point, because we have a curve, right? So a curve is made up, I can't really get the slope. It's not the same throughout the whole graph because the slope is changing. So that's the difference between the two. Okay, so going back to the notes, here is the average rate. All I do is take from this point to this point, even though it's not a straight line, I pretend it's a straight line, okay? Pretend it's a straight line, and I take the change in x over the change in t, okay? For my instantaneous rate, the instantaneous rate is the tangent to the curve at any given time. So which time am I talking about in this picture? Okay, that's a pretty good version. Right where the two are parallel. So at this particular time, this triangle here, the rise over the run, represents the instantaneous rate. Okay? All right, well, you know this if you've taken a calculus course or a pre-calculus course or you're on your way to calculus. Let me make this smaller. As my delta t gets smaller and I make my little triangle smaller and smaller and smaller and smaller, my average rate will approach my instantaneous rate as my change in temperature goes down. So what are we going to do in chemistry class? Which rate are we going to measure? At which time should we measure the rate? Well, the best place to measure it is right out of the box, because at that point, the concentration of the reactants is not dropping yet, right? They just started to react. So if you can measure it in the first few seconds of the reaction, you're going to get the best results. So that's the number we're going to use. Our rates that we're going to talk about now are going to be the instantaneous rate of the chemical reaction at the start of the reaction. So we'll call that the initial rate, and we'll put a little 0 for the initial concentration and the initial time. So it's going to be the rate of the reaction is a function of how much time has elapsed since the start of the reaction, right? It's constantly dropping. So where do we want to measure it? We want to measure it right out of the box. So the numbers I'm going to give you for rate are going to be the instantaneous rate. Okay, I know it's a little tricky. Right? Here we're watching A drop. I don't want to measure it way out here because I don't know what the concentration of A is necessarily. But right out of the box, if I blew this up, I want to measure the rate right when it starts, in that first few seconds. If I did the slope of the line in those first couple of seconds, it approximates a straight line here too, right? Right out of the box in that first couple of seconds. Can't wait too long because here the concentration is changing. With C, can't see it anymore because I drew all over it, right? But C looked like this. Okay, I'll make it. So when do we want to measure it? Right in the beginning, those first couple of seconds. Those are going to give us the best results. Okay? All right, so if you have the concentration of, or the rate of change of one of the reactants, like how does A change with time? and you know the stoichiometry of the chemical reaction, you can calculate the rate of change for any of the other reactants or products. So this section, this section is called Relating the Different Ways of Expressing Reaction Rates. Okay, so here we have a general chemical reaction. The capital letters represent the individual chemicals that are reacting. So A is going to react with B and C to form D and E. Capital A, capital B, and capital C are the names of the reactants. Okay, so if this was a real chemical reaction, this would be water plus carbon dioxide plus oxygen. Goes to making hydrogen peroxide and methane, whatever the particular chemicals are. Okay? All right, so that's the first thing. Second thing is, if you have a balanced chemical reaction, these numbers are going to be the coefficients. So this might, if this is water, this might say 2 waters react with 1 carbon dioxide and 1 methane to make 1 hydrogen peroxide and 1 something else. Okay? So these numbers, the small a's, b's, c's, and d's, are the coefficients of the balanced chemical equation. Okay, so this little formula here gives you the relationship between any one reactant and any other reactant, any one reactant and any product, or any 2 products. Okay, so you're basically going to relate the thing that you know about, the thing that you were able to measure, to the one that you're interested in. So for a second, let's just concentrate on A and B. Okay, if I concentrate on A and B, the way this works is minus 1 over the coefficient. So if, let's say this was a 2 here, I'd put a 2 down here, times the change in the concentration of A with time is equal to minus 1 over the coefficient of B. Let's say that was a 3 here, I'd put 1/3 times the change in concentration of B with time. So if I cover everything else up and I was just measuring the relationship between A and B, there's my relationship. I look at these two, just 2 at a time. Well, this should make sense. Why the minus signs? Because they're reactants. They're disappearing. Look at A, B, and C. They all have minus signs because they're reactants. Reactants disappear. So don't be surprised when their concentration drops with time. So this number here will come out negative, right? Because the concentration is going to be less after a certain amount of time than it was before. So I'm going to need a negative to balance that negative. So I put negatives on both of the reactants. Okay? How about the products? The products grow in. How fast do they grow in? Well, they grow in, right? The relationship between D and E is that if I want to see the relationship between D and E, and this is a 5 here, and this is a 2 here, I say 1/5 times the change in concentration of D with time is equal to 1/2 the change of concentration of E with time. So all I do is take the coefficients here and here and put them in the denominator. Why does D, E, F, G, anything that's a reactant have a positive sign? Because they're products. The products are going to have positives. The reactants are going to have negatives. Okay, let's see if this makes sense to us. Okay, let's do a 1 and a 2 situation here with A and B and see if it makes sense. Okay, if A has a 1 in front of it and B has a 2 in front of it, then common sense would tell you that B, right, that B would be dropping twice as fast as A, because every time one of these chemical reactions occur, you use up 1 A, but you use up twice as many B's. Okay, so that's why you need the 1/2 here. If I want to know the concentration of B with time, and A was 1 and B is 2, then I'd get a 1 here, 1 over 1 is 1, and here I would have a 1/2. Well, what is B then? If I were to solve that for B, it's going to look like this. The change of B with time is going to be equal to, if this is 1/2 and this is 1, what happens to the 1/2? I cross multiply and I get a 2 in the denominator. It's going to be twice as much as the change in concentration of A with time. Okay, these guys both have negative signs on them. If they both have negative signs on them, I can cancel out the negative signs, and I get this relationship. Okay, let's see if it makes sense. So the formula will always work for you. So how will you see this on a test? Well, I might give you the concentration change, the rate of reaction in terms of A, and ask you for B. So all you'd have to do is multiply the change in A by 2, and you'd get the change in B. Well, let's see if this makes sense for our chemical reaction, right? We said that our reaction was A plus 2B go on to make products. We don't care which the products are right now. We're just looking at the relationship here to here. Okay? So one with respect to another. Does this make sense? Okay? For every A that disappears, twice as many B's disappear. So if I know how fast A's are disappearing, I should multiply them by 2 to get how much B's are disappearing. So the rate puts these coefficients on the other guy when you're relating one thing to another. It's the opposite of stoichiometry. Okay? All right. Let's do the relationship. Let me see if I have some real ones. Yeah, I have some real ones, so I won't do any more. Okay? So, take-home lesson. Let's blow this up a little bit. This is an important skill. When you're relating any reactant to any other reactant or any product, reactants get a negative sign in front of them, and you put a 1 over their coefficient in front. If you do that, for each two things you're relating, let's say you're relating this one and this one, then you just put those parts together, okay? For instance, what's the relationship between A and D? Well, this one's dropping and this one's going up, so I'm going to have one of them have a negative sign and the other one have a positive sign. They're going to have the opposite sign, of course, because A is going to be going down. So when I do the experiment, I'm going to get a negative number. B is going to be growing. Okay, and what is the relationship? I just need to multiply the A part by 1 over A and the B part by 1 over, the D part by 1 over D, small d, the coefficients. Okay, all right, so take a look at that for a second, absorb it. Okay, that's the general formula. Then we're going to do an example. Okay, so that covers any general situation. Okay, make this a little smaller, and we'll do an example. Okay, this is a gas phase chemical reaction. 2 nitrogen dioxides react with a fluorine gas to make 2 NO2F gas. Okay? All right, let's blindly follow our rules, right? So what is the relationship between the rate at which this disappears, the rate at which this disappears, and the rate at which this appears? Well, anything that's a reactant gets a negative sign, and then the 2 becomes 1 over 2 here. The fluoride has a coefficient of 1. Fluorine has a coefficient of 1, so I just have a negative 1 over 1 is just 1. The NO2F has a coefficient of 2, and it's a product. So it's a positive sign because it's a product, and it has a 1/2. Okay? I'm never going to use all 3 at the same time. I'm going to give you one and ask you for the other one. So let's take a look at the relationship. What's the relationship between the disappearance of NO2 and the and the disappearance of fluorine? Okay, well, if I put these two things together, where this happens to my one, I got a negative sign and a negative sign, so they cancel out. And then to get rid of this 2 in the denominator, multiply both sides by 2, and I get this relationship. Let's see if that makes sense. The rate at which nitrogen dioxide disappears is twice as fast as the rate at which fluorine disappears. Hell yeah, that makes sense to me. That's got a big fat 2 on it, right? The rate at which this stuff is going to come into the picture is going to be twice as fast as the other guy, because this guy's growing twice as fast, because every time a collision happens that's fruitful, that goes on to products, I get 2 of these for every one of these. Okay. Next relationship. What's the relationship between NO2 and the product? Well, take this guy and hook it up with that guy. Leave the middle one out. One has a positive sign, one has a negative sign. That's why they have opposite signs. But they both have a coefficient of 1/2. So if they both have a coefficient of 1/2, the 1/2s cancel out. So the rate at which nitrogen dioxide disappears is equal to the rate at which nitrogen NO2F appears. They are equal in magnitude but opposite in sign. Why? They have the same coefficient. This one is disappearing as fast as this one is appearing. So the only difference is the sign. Okay, last relationship. This guy and this guy. Okay? This guy's going to have a negative sign, and he's going to have 1/1 is 1. This guy's going to have a positive sign, and he's going to have a 1/2. Okay? Well, if I take that, that's that relationship, right? I need to keep my negative sign because one is negative, one is positive. They're not going to cancel out like in the first case. Here, they both were negative, so they canceled out. The relationship between those two, right? Why does this guy get a 2 in front of it? Because I just brought the 2 over to the other side. Okay, let's see if it makes sense. The rate at which the product is formed, the nitrogen, the NO2F is formed, is equal to negative 2 times the rate at which the fluoride disappears. Yes, because this guy has a coefficient of 2. It's going to grow in twice as fast as this one. Okay? Good. This is how they relate to one another. So you can grab any situation you want and relate them back to one another. Okay? Let me give you one more. I will make it up. How about we do, I'm just going to do Z's. 7x plus 5z's react to make 2 w's. Okay? If I told you I know that the rate at which the w appears with time is equal to 13.2 molarity per second. Okay? This is the change in molarity with time. That's a typical unit for rate. Molarity per second. Not moles per second, moles per liter per second. Molarity per second. Okay, so I know that one. And I want to know, I'm interested in what's happening with x. How does x decrease with time? Well, if I have one, I can relate it to the other. So first, let's put it into the formula. Okay, so if I want to know this one, based on this one. Right, am I going to do anything with the z? No. They asked me about x, and they gave me w. Okay, if I want to find this out, what do I do with the 2 and the 7? One's going to be positive, one's going to be negative. Let's see. Okay, so first thing I do is I just write out my equation, right? What did we just learn? Well, we just learned that 1/7 times the change in concentration of x with time, with a negative sign in front of it because it's a reactant, is equal to positive 1/2, because of that 2, times the change in the W concentration with time. I gave you this one. So you just plug that guy right in here and solve it for the change in the concentration of X with time. So to do that, I get this. The negative 1/7. Okay, what happens to the negative? I multiply both sides through by -1. This -1 cancels. I get a negative over here. And what happens to the 7? I want to get rid of 7 on this side, 1/7. I multiply both sides by 7. They cancel out over here. So I get 7/2 the concentration of W with time. Last step, just plug in the number, multiply it by 7/2, and change the sign. Okay? So I'll do that for you. The change in X with time should be equal to -7/2 times 13.2 molarity per second. Okay. All right, 7 divided by 2 is 3.5. 3.5 times 13.2 is equal to 46.2 molarity per second. And the last thing is I just need my negative sign, right? Because X is disappearing. X is going to disappear 3.5 times faster than W appears, because it's got a coefficient of 7. What's the relationship between 7 and 2? This guy should disappear 3.5 times faster, or 7/2 times faster than the other guy. Okay? This has one too many significant digits based on this. Oh, I had 3 there, and I have 3 here. I'm okay. It's perfect. Okay, leave it alone. Good? Okay. Switching gears now to probably the most important topic in the chapter is the dependence of the rate on concentration. So we're going to define now something called the rate law. Okay? So the rate law is an equation that you can write in which you can always figure out the rate of the chemical reaction, how fast it's happening, if you know how fast the reactants, you know the initial concentrations of the reactants, okay, and a rate constant, okay? So it's always going to take this form. The rate law will take a form that looks like this. Let me read this first, and then we'll go down to here. So the rate law is an equation that relates the rate of a reaction to the concentrations of the reactions and catalysts raised to various powers. Now, the key to this is the powers that the molar concentration of A and molar concentration of B are going to be raised to, you don't know yet, okay? You don't know them yet. You're going to have to figure them out experimentally, okay? So all you can do at this point until I teach you how to do these, look at this data and look at the experimental data to figure it out, all you're going to be able to do if I give you a chemical reaction like this is say the rate of that chemical reaction, no matter what I'm following the disappearance of A or the disappearance of B or the creation of C or the creation of D. The rate will always have this form. It will be equal to some rate constant times the concentration of any of the reactants. We only have 2 reactants, A and B. You leave C and D out. How much is in the pile of products don't matter, because it's A and B that have to hit one another to react. To powers that we will determine in a little while. So just raise it to the X, the Y. What happens if you have 3 things over here, A, B, and C? You need A, B, and C to the X power, the Y power, and the Z power. So first, just set up this rate law, okay? All right, now, these little zeros mean the initial concentration right out of the gate, right when I start the reactions, okay? This is the rate constant. We're going to show you how to do that. All right, these exponents, which are not the coefficients, there might be a coefficient of 2 here, there might be a coefficient of 3 here. If this is an overall reaction and not necessarily a molecular reaction, you just have the overall reaction, you don't know what they are. Don't assume they're the coefficient. Just because this has a 2 out in front of it, don't make this a 2, okay? They are called the order of the reaction. So X and Y, and if you had another thing, Z, are going to be the following kinds of numbers. They're going to be, something could be to the 0 power, right? That means it doesn't matter. Something can be to the 1st power, 2nd power, 3rd power, 1/2 power. The only other one you'll ever really see is the -1 power. Those are going to be the typical culprits that these initial concentrations are going to be raised to so that you can calculate the rate. Okay, so one more time. The rate law is always going to take the form. Rate is equal to a rate constant times the concentration of any of the reactants to powers that we will determine later. The powers that we will determine later are integers like 0, 1, 2, 3, 1/2, which is the square root power, and -1. That's pretty much the only ones you're going to see. Okay? -1 is interesting, and we'll see why. Okay? Now, we're almost done, right? How are we going to figure out what X and Y are? Well, I'm going to give you data. Based on the data, you're going to fish out what those what those exponents are. So scientists set up a series of chemical reactions where they purposefully change the concentration in the second experiment compared to the first so they can use that data to figure out what X is. Then they take a third experiment and a fourth experiment and set them up in such a way that when you look at one related to the other, you'll be able to figure out what Y is. Now, if there was a third term here, a C, and we had to figure out Z, a third exponent, you'd need another 2 experiments. So you pick the experiments that you want to look at to help you figure out what X and Y are by inspection. Okay? And what are those X's and Y? They're called the order of the reaction. Okay. All right, let's first talk about the rate constant, okay? And then we'll go back and I'll show you how to work with the data. So I'll make this a little smaller. Okay, so the rate constant is given the symbol small k. There it is. So rate is always equal to the rate constant, concentration of A to some power, concentration of B to some power. What is K? K is the proportionality constant in the relationship between rate and concentration. Remember, the real science is the fact that when you change the initial concentration of A to some power, what does that do to the rate? Does it double the rate? Does it quadruple the rate? Really, all the interesting stuff is over here. But whenever you have one thing is proportional to another, there's always a proportionality constant, right? If I have, when this goes up, this stuff goes up, I can always multiply it by a number, right? Multiply it by a number so that it's not just this stuff is proportional to this stuff, you can get this stuff equal to this stuff. So that's what a proportionality constant does. It's the constant that you would get if you brought all this stuff over to the other side. Rate divided by these two would always give you that rate constant as long as you didn't change the temperature. So that's important. Rate constant is very much a function of temperature. We're going to leave it the temperature in our series of experiments exactly the same. Okay? Can't be changing the temperature while we're trying to figure out what X and Y are. We got to do one thing at a time. Okay, so back to what K is, the rate constant. It's a proportionality constant in the relationship between rate and concentration. Okay, it has a fixed value at any given temperature, but varies a lot with temperature. Okay, very much a function of temperature because the molecules are going to hit more often. When it's higher temperature, they're going to hit harder, and there's going to be more fruitful reactions. So 99% of the time, in fact, honestly, 100% of the time, the rate constant will go up with an increase in temperature. Okay, typical units for the rate are going to be either moles per liter per second, or what I like better is molarity per second, concentration per second. Okay, you're always following one substance at a time. So it's the change in concentration over time. So units would be molarity per unit time. Okay, the rate constant then, so this is the units on rate. The rate constant is going to depend on the form of the rate law. Okay, so we'll dig them out in individual cases in a little while, and you'll see there'll start to be a pattern, and I'll write down what that pattern is, but I don't want to overwhelm you. The rate constant in a first order reaction, something that just has A to the first power and doesn't have anything for B because B is to the 0 power, is going to be different than if this is a 1 and this is a 1. Okay? So it's going to depend on the situation. Okay, the reaction order with respect to each given reactant species equals the exponent of the concentration of that species in the rate law as determined experimentally. So for instance, if I figure out that X is 1, then I would say the order of the reaction in A is first order, if this is 1. If X turns out to be 2, I'd say the order of the reaction in A is 2. If B, right, if Y turns out to be -1, I would say the order of the reaction in B is -1, okay? If B turns out to be 0 order, doesn't matter, right? Something to the 0 power just puts a 1. That means changing the concentration of B does not affect how fast the chemical reaction happens. That happens a lot, okay? If this guy turns out to be 0, and I wanted to describe it to everybody, I would say the order of the reaction in B is 0. So mostly, you're going to have things being first order, second order, 0 order. Very rarely you will have 3. Once in a while you have -1, and once in a while you'll have 1/2. Okay? So when someone's talking about the order of the reaction, they're talking about the X's and the Y's. Okay, so those are for the individual orders of the reaction. Okay? So X is the order of the reaction with respect to the concentration of A. And again, the best place to do it is right out of the gate, the initial concentration. That's where we're going to do our experiments. Y is the order of the reaction with respect to B. Okay, what's the overall order for the whole chemical reaction? It's just the sum of the individual orders, X plus Y. So if X is 1 and Y is 1, the order of the overall reaction is 2. 1 plus 1 is 2. If X is 1 and Y is 0, 1 plus 0 equals 1, you'd say it's a first order reaction overall. If B is 1 and, if Y is 1 and X is 0, it would also be the overall order of the reaction would be first order. Okay, so the overall order is just the sum of X and Y, the individual orders. Okay. Now, if you have 3 things, if your chemical reaction was fancier and it had A, B, and C, then it would be the sum of X, Y, and Z. Okay, let's look at a experiment here, okay? And this experiment is a little different than the ones that you're going to see on the test because I made it easier. I gave you what the rate is and I told you what the orders are. So it's a little different. In general, that's your job is going to be to figure out that it's first order in bromine, first order in bromate, and second order in hydrogen. Okay? But in our case, I'm going to give you that. So let me read the example all the way through and let's do it. Okay? Let me just focus a little bit. Okay. Example. Bromide ion, that's this stuff, is oxidized by bromate ion in aqueous solution. The experimentally determined rate law is the rate of the reaction. Okay. Now, I could be following whatever I happen to be following. It doesn't matter. I could be following the disappearance of this, the disappearance of this, the disappearance of this, the appearance of this, or the appearance of that. We're just going to call it rate for right now. So I'm following one of those. Okay? All right. So the rate is equal to the rate constant times the concentration of any of the reactants, there they are, bromide, bromate, hydrogen ion, to powers that are either given to you or you figured out experimentally. We were given them. You're told that it's first order in bromide, first order in bromate, and second order in hydrogen ion. So the first question, they give you this, this, and this. What's the overall order? Well, that's easy. 2 plus 1 plus 1 equals 4. You just add up the exponents. The overall order for this chemical reaction's kinetics, or its rate, is 4th order. Last thing, what would K be? Well, if I knew what this rate is, I determined it experimentally, and I knew the rate of the reaction under initial concentrations of bromide, bromate, and hydrogen ions, I knew what I put into the beaker before I started, I could calculate K, because this I can measure. I have some kind of tool that shows me the speed. Usually, in this case, you could follow a pH meter to watch as hydrogen ions appear or disappear, because this guy, a pH meter measures hydrogen ions. Okay, so if the reaction was happening, I'd watch the H plus disappear and the pH would go up. Okay, so if I knew this, this, and this, and the overall rate constant, I knew the rate, how could I get the, and I wanted to calculate the rate constant, I could just solve this for K. So bring all this underneath rate, and I'd get K is equal to the rate divided by the bromine concentration, the bromate concentration, the hydrogen ion concentration. These two are to the first power, because that's what they gave you up here. These two are to the 0 power. I didn't do anything. I just took this and did algebra to get that. Okay, let's take a look at the rate on this case when it's fourth order. Well, when it's fourth order, what are the units of rate? Well, I don't care which thing I'm measuring, appear or disappear, rate always has molarity per second. Okay, well, what is K then? Let's see what its units. This guy has molarity per second in the numerator, and it's got molarity to the first, and molarity to the second here. So wow, that's 4 molarities. Molarity times molarity squared. That would be molarity to the 4th power. So I have 1 molarity in the numerator and 4 molarities in the denominator. So one of these cancels with this one here, cancels with that one there, and I get my units. This seconds is in the denominator, and this molarity is in the denominator. This is not the denominator of the denominator, right? This is just the regular denominator, so it stays in the denominator. Okay, so I could do it and put one step in between to make it a little easier for you. So what happens here is that M cancels with one of those M's over there. So for a split second, I have this. But that's super ugly, right? So how can I fix that? This is the same thing as this, right? Because multiplying by 1 over something is the same thing as putting it in the denominator. Okay, and then the last step, instead of showing the molarity to the 3rd power and the seconds to the 3rd power in the denominator, I could write that as anything, whatever the power is, something in the denominator is to the negative that number, right? So that would be the same thing. This is the way you usually see it, right? You're not going to have this too often. This is really complicated because very few chemical reactions have an overall order of 4th. Usually it's something more like 1st or 2nd. But look what happens. There's a scenario here, right? Whenever K, what's the units on K? You're always going to have a second to the -1 for any kind of K, but you're going to have 1 less molarity in the denominator than whatever the order is, okay? Always you're going to have 1 less. So let me make a little chart for you. I'll get a piece of loose leaf and I'll make a little chart for you because I usually do it in class. And it'll explain each situation, okay? What do you do when the overall order is 1st? What do you do when the overall order is 2nd? What do you do when it's 3rd? What do you do when it's 4th? And we just did the one for 4th. Now, you don't have to do that because you can just plug in the numbers every time and get the answer, okay? But let's go ahead and do that. And then I'll do this check here, okay? All right, so let me get some loose leaf. Okay, we just did the 4th order situation, right? So we did one of the harder ones. Let's go back to the beginning. What happens if the overall order of the chemical reaction is 0, you don't have any chemistry, okay? So that can't happen. So at the minimum, something has got to be, it's got to be 1st order, okay? So this is going to be overall order. First, 2nd, 3rd, and 4th, okay? And you could keep going, but you're not going to see those cases. All right, well, I know this one is molarity to the -3, seconds to the -1. This one is just going to be seconds to the -1. So let's see if we can fill in the pattern. I got to get to molarity to the minus 3 here. This one is going to be molarity to the minus 1, seconds to the minus 1. You always have one less molarity than this guy here. Okay, this one doesn't have any in the numerator. This guy has one less. Okay, what about third order? Molarity to the minus 2, seconds to the minus 1. So you see the pattern develop. You always have one less. Why? Because you need 2 of the 3 molarities to cancel so that the rate comes out to molarity per second. Rate is always going to be molarity per second. So this is overall order. And then this is going to be the units on K. What is K? The rate constant. Okay? The units on rate are always the same. Units on rate, molarity per second, molarity per second, molarity per second, molarity per second, or molarity times seconds to the minus 1. Okay? Right? Everybody agree? That's the same thing. Each of these could also be written like that. Molarity times seconds to the minus 1. So I'll leave this up for a second. I'll make it nice and neat if you want to take a picture. Make it a little smaller. All right? These are foolproof. They'll get you through each situation. Okay? Again, you don't have to even memorize it, but you should just recognize that's what your expectation should be once you're done with the math. Okay. Let's see what happened when we plug everything back in. Rate, we know, always has to come out to molarity per second. We just said that when the overall order is fourth, I need the units on the rate constant to be molarity to the minus 3 times seconds to the minus 1. So this is this. Okay? Okay, what is the units on bromine to the first power? Just molarity, right? This, anything in brackets, is concentration to molarity. Bromate is also an M. Hydrogen ion is M squared. So I have 4 molarities here, right? 4 molarities in the numerator. I have molarity to the fourth times molarity to the minus 3. What happens when you have that? Molarity to the fourth times molarity to the minus 3. How do you deal with multiplying 2 numbers that have exponents? You add the exponents. So 4 plus a minus 3 gives you molarity to the first. 4 minus 3 is minus 1. Okay? Or I should say 4 minus 3 is 1. Okay? And it also had seconds here. Or if you wanted to write it with the seconds to the minus 1 here, you'd get seconds to the minus 1. So that way, that's the same thing. This and this are the same thing. Good? All right, so what did we just prove here? This is the bottom of the notes, page 7, is that the rate, if you do all the algebra right, the units on rate will be the same as everything in the rate law when you put it in. The rate constant times the concentrations. This is a particular case. It's an exaggerated case. Most of the time, our orders are going to be second order overall, first order overall, maybe third, right? Fourth is pretty far up there. That's unusual in chemistry to have 4 particles come together at the same time and kind of collide. Not going to happen too often. Okay. All right. Still didn't teach you how to figure out what X, Y, and Z are, right? I just told you them in this question. I just told you X, Y, and Z were 1, 1, and 2. So the next example, that's what I'm going to show you. How to determine the orders of each reactant given a table of experiments. Okay, let's just read this. The rate constant has the units that leave the rate with molarity per second. We knew that. Okay, so super important section, right? If you need to take a break, take one and come back to it. Super important section. Determining the rate law from initial rates. Okay, typical question. I give you the overall chemical reaction. Two dinitrogen pentoxides in the gas phase react to make 4 nitrogen dioxides and oxygen. I do 2 experiments, okay? In the first experiment, I start out with the initial concentration of dinitrogen pentoxide in the reaction chamber as 0.010 molarity per second. Excuse me, molarity, okay? So if I wanted to think about this, since this is a gas phase, I could think about it as having a 1 liter vessel. And in my 1 liter vessel, here's my reactants, the N2O5s. And what's the concentration? If this vessel is 1 liter, how many of them do I have in there? I have 1 mole, right? Because 1 mole per liter will give me a 1 molar concentration. Okay, so I could do this in a, it doesn't matter the size of the reaction, but in my head, I might as well think about it as a 1 liter vessel. Okay, so that's the initial concentration. Okay, I do the experiment. I follow. Now you always get a choice as to what to follow. So I follow the drop in N2O5 with time, right? Got a negative sign in front of it because I know it's going down. So the reason why these numbers here are expressed as positives is because I have my negative sign up here. Okay, so negative this is equal to that. Okay, I do the reaction and I measure the rate. Now this I could measure with the spectrophotometer because N2O5 has a color to it. So I could watch it disappear because I could watch that color drop. These two things don't have any color to them. So just with a colorimeter, I could watch the concentration change with time. And I could get this rate, okay? Because this guy is going to be dropping. It's a reactant. Then I repeat the experiment at the same exact temperature. This time I double the concentration. If I double the concentration, maybe it's going to go faster because there's more molecules in the vessel. There's going to be twice as many. So I've got to make twice as many X's. It's got double the concentration. They should hit each other more often and maybe give me a faster rate. Well, let's see what happens. When I doubled the concentration, what happened is I went from 4.8 times 10 to the minus 6th to 9.6 times 10 to the minus 6th. So doubling the concentration doubled the rate. So what we're doing right now is we're going to do it by inspection. Okay? Anytime I see that happen, that whatever I do over here, when I purposefully change this to twice as much, leaving everything else constant. Now this is easy because there's only one thing in the reactant. So I doubled this and I saw doubling over here. Now I know what you want to say. You want to say the order of the reaction is going to be second order because doubling. No! Whenever you get the same effect here, whatever you do over here, you get the same effect over here. That's first order. That's something to the first power. That's a linear relationship. If I would have tripled this, I would have gotten a tripling over here. So I'm just changing the experiment that I'm choosing. Okay? I did an experiment, I got a certain rate. I did the experiment over with twice the concentration, I got twice the rate. I have just proved that I have a linear relationship. What I do here gives me the same effect here. First order, first order, first order. Same thing. What you do as a scientist, you choose to double the concentration, you get a doubling when you look at the results. Okay? I've just figured out that X is first order. Okay? First two things then that I should do. We're choosing to identify the rate of the reaction as the dropping of N2O5 over time. I could relate that to this and this as I already showed you, right? How does this guy grow in? It should grow in twice as fast as this guy disappears. How should this guy grow in? Half as fast, because this is 2 to 1. Okay? That's a different question. That's what we did before. Right now, though, I can figure out the rate law. I've just figured out that the rate for any chemical reaction, in fact, I could have wrote this part first. The rate for any chemical reaction is equal to the rate constant that I'll determine in a little while, times the initial concentration of any reactants. This chemical reaction only has one reactant, N2O5. So I write that down to some power that I'm going to determine later. Well, I just did. First I put X, but I quickly replace X with a big fat number 1 because I proved that this was linear. What I do over here, I get over here. Okay? Relationship here to here. That's first order. Okay? Double the concentration gives you a doubling the rate. Don't put 2. Okay? It's 1. The overall order for the reaction is 1. There's no other reactant. There's only N2O5. So I don't have to worry about what Y is. There is no Y. Okay? So that was an easy example. Last step. We figured out the overall order is first order. Now that I know the rate at a particular concentration and I know the rate law, look what I could do. I could figure out what K is by taking one of the experimental results for rate along with the concentration that gave you that rate and solve for K. You should get the same value for K whether you pick the first experiment and plug in the data, now that you know the rate law, or the second experiment and plug in the data. Either one. Just don't do this. Don't do halfway, right? Don't do this guy and this guy or this guy and this guy. Pick one line. Go straight across. We know X is 1 now, right? I'm going to pick the top one. I'm going to pick the rate here, plug it in here, pick the concentration that went along with that rate, and solve for K. So K is equal to the rate divided by the concentration of N2O5 to the first power because we figured out that X was 1. So K is a constant. It's not a function of the change in concentration. Plug it in. I did it for experiment 1. I take my 4.8 times 10 to the minus 6 divided by 0.01 molar. K, molarity, cancels out with molarity, and I get seconds to the minus 1 as the units on rate constant. 4.8 times 10 to the minus 6 divided by 0.01 gives you 4.8 times 10 to the minus 4. You could have also done it just as well with experiment 2. Just be consistent. Take this number for the rate, this number for the concentration, plug it into the formula we just learned, right? K is equal to the rate in that experiment divided by the concentration in that same experiment to the first power. So this divided by its concentration. This divided by its concentration. Take these off of here. Oops. I get the same exact number. You might not get exactly the same, you should get very close. And again, molarity cancels with molarity, and I'm left with seconds to the minus 1. Well, what did I just show you? I'm going to go back to that. Whenever the overall order of the reaction is first order, what is our expectation for the units on the rate constant? It should be seconds to the minus 1. Because if this is molarity and this is seconds to the minus 1, you're going to get molarity times seconds to the minus 1, which is good because that's the rate, the units on rate. Okay, so seconds to the minus 1 is what we learned. Whenever the overall order is first order, my expectation for the units on rate are seconds to the minus 1. Okay. That was doing it by inspection. Another way you could do it is to, if you didn't see right away what was happening, you could take the rate in any one experiment and plug in the rate law for it and just leave the x's in there. Take the rate in the other experiment, plug in all of those numbers and solve for x. And I'll show you how to do that. So what we're going to do is I'm going to take the second experiment and I'm going to divide it by the first experiment, right? You can always take a series of numbers and divide it by something else, right? We're going to make a ratio of one thing to another. So, hey, why am I taking the second set of data and dividing it by the first set of data? Because it's bigger. It's twice as big. So I could see I'd rather work with numbers like 2 than 1/2. So this guy's information divided by this guy's information, okay? Assume now that we didn't do it by inspection. I didn't easily see that as this doubles, this doubles. Most of the time on the test, you're going to do it by inspection, okay? But let me show you the foolproof way. Okay, so I say for experiment 2, we know that this is always true. Rate is equal to a rate constant times the initial concentration of whatever the reactants are to the x power. Well, for the first experiment, rate is equal to that same constant times the initial concentration to the x power. These numbers change, but x is still x. X is the order in which the reaction is raised to. That is not a function of what the amount of stuff that the scientist chooses to put in the experiment. So what happens is, well, let's put in the numbers and see. Put everything in for the second set, everything in for the first set. I get this. Okay, well, first thing that happens is I've got a k in the numerator and k in the denominator, so they cancel out. Second thing that I notice is that I can take this number, it's just a number, and I can divide it by this number, and I get a big fat 2. This number is twice as big as that number. All the units cancel out. Okay? Next, take this number, anything, raised to the x, divided by anything also raised to the x. What does a rule in math say? That if you have something to the x divided by something to the x, it's the same as the whole thing to the x power. I don't have any idea yet what x is. I didn't do it by inspection yet. But I do know that this relationship holds. Something to the x divided by something else to the x, same as the whole thing to the x power. Okay, how am I going to determine what x is? Well, first of all, you can do the math inside here. You don't know what x is, but 0.02 divided by 0.01 is a big fat 2. So now you have 2 is equal to 2 to the x. Well, you can guess at it. What's the value of x? X must be equal to 1. Okay? So this is the mathematical way of doing what we did by inspection. What was by inspection? Just comparing them, which is my suggestion to you, is look at this. I doubled the concentration. What happened to the rate? That's inspection. Here's the mathematical way of doing it. If you ever get something weird here that you can't just easily look at it and say, oh, x has to be the first power. Well, what would happen if this outside of here, if this would have been a 4? Well, I'd have 4 is equal to 2 to the x. I'd say, oh, I know what that is. That's 2 squared. It would have been second order because the rate would have been 4 times bigger by doubling the concentration. Okay? Here, it's first order because 2 is equal to 2 to the x. X has got to be 1. Okay? If you don't see that, the only other thing you can do is take the log of both sides and it'll bring the x down and then the 2's cancel out and you'll get 1. Okay? So just for those people who don't see that, I'll do that really quickly. If you get weird numbers, you take 2 is equal to 2 to the x. So if I had like 52 and 57, they weren't exactly the same, I could say, oh, how am I going to get something out? I could take either the log or the ln of both sides. The ln of 2 is equal to the ln of 2 to the x. Now logs have this very interesting property that the log of a number to the x is the same as ln of 2 where x becomes the coefficient. Remember that? That's something you learn, I think, in intermediate algebra or pre-calculus. Okay, well, how do you get x? Divide both sides by ln of 2. This cancels. And what's a number, the same thing divided by itself? Big fat 1, so x is equal to 1. Okay, so obviously you don't have to go through all that work. You would only go through that, let's say this was like 2.7 and this was like 2.4. So it wasn't experimentally perfect and you wanted to see what you get for x. You'll remember x's, y's, and z's should be whole numbers, or we had a set of possible orders of the reaction. First order is very typical, second order is very typical, zero order is very typical, negative first order, and 1/2. That's about it. It's got to be one of those. Those are the typical orders of the reaction. In one of the in the chemical species, whatever you're talking about, A, B, C, or D. Okay, in one of the reactants. Okay, let's do another one. This time we're going to do it completely by inspection, and we'll take a break right after that. That'll be the end of this video. Okay, very typical, great test question. Okay, peroxide plus iodine plus hydrogen gives you iodate and 2 waters. Okay, or triiodide and 2 waters. Scientists choose to do the following 4 experiments. Okay, in the first experiment, they take an initial concentration of peroxide, initial concentration of iodine, initial concentration of H+, put them into the beaker, hit the stopwatch, see how fast the reaction occurs. Right? It doesn't even matter. We're not even going to talk about which one of these things we're going to choose to monitor. Honestly, we're probably monitoring this because this guy is blue. So we'd watch the solution slowly turn blue. Okay? But we're just going to call whatever we're monitoring the rate. So the rate of the chemical reaction are these numbers. So that's an experiment. You do that. Then you come back. You do that experiment. Then you come back. You do that experiment. Then you go to lunch. In the afternoon, you do the 4th one. So these are 4 separate experiments, but we're going to take the data from those 4 separate experiments and use it to figure out what the rate is. Okay, very first step. I give you all this stuff. First thing I'm going to ask you is, what is the rate law? Okay, boom. The rate law is always the rate of a chemical reaction is equal to some rate constant multiplied by the concentration of any of the reactants. These 3 things. To powers that we will determine later. So why peroxide? Because it's there. Why iodine? Because it's there. Why hydrogen? Because it's there. I don't know X, Y, and Z yet. I'm going to use this data table to figure them out. That's the general rate law for something. Don't put products in. It's not equilibrium. Don't put them in the denominator. These don't matter. How fast something is going to occur depends on the concentration of the reactants, because the reactants have to hit each other to make the products. Okay, so that's easy. You get points for that. Okay, so just write down the general rate law. Next step, you need to figure out X, Y, and Z. This is Y. Okay, this guy, a little hard to see, this guy's Y. All right, now, here's what I do. I look at places where I have commonality and something else is held constant. So these scientists did a great job. They gave us sets of reactions where I could factor one of the concentrations out and measure what's happening with the other ones. So let's take a look at experiment 1 and 2 first. In experiment 1 and 2, we purposefully left this guy the same. So if it's the same, it's not going to affect the rate. If this is the same exact number, right? I purposefully kept them the same. So this is an affecting rate, this is an affecting rate, but this is. So let me ask the question, what happens to the rate of the chemical reaction when I double the peroxide, but I hold everything else constant? When I double this, I double that. That's a first order relationship. Whenever what I do over here, I get the same exact effect over here, that's called first order. Okay? So same effect. If I would have multiplied this by 10 and got a tenfold effect over here, that's not 10th order. When I get the same thing, that's first order. Okay? So we've just figured out that for our rate law, X is an X. X is a big fat 1. It's first order because I doubled the concentration. I got a doubling in the rate. Boom. First order. So now X is done. Okay, let's see if the scientists set it up for us nicely that I can use another 2 experiments to work on Y. What's Y? Y was the effect of the concentration on iodine. Well, let's look for a place where I changes, I minus changes, but the other two bad boys are held constant. So looking around, okay, that looks pretty good. That guy's doubling. Oh, wait a minute, but that one and that one changes too. It's too complicated. This guy stays the same. So I'm not going to take 2 and 3. How about 1 and 3? Yeah, that's it. 1 and 3. These two guys are the same. These two guys are the same. So the only thing I'm changing is the I minus. Well, what did we do? We doubled. Okay, you don't have to double. The scientist is a free country. They could quadruple. But let me see, when I double this, what happens to the rate? It also doubled. So it's first order in peroxide, and we've just figured out it's also first order in I minus, because when I double the concentration, keeping everything else constant, I get a doubling of the rate. Isn't 2.3 times 10 to the minus 6 double 1.15? So now I got 2 of these guys. I just figured out that not only is X 1, but Y is also 1. From experiment 1 and 3, I minus is doubled and the rate is doubled. Okay, I got one more partner to do. Let's look at 1 and 4. Well, let's not guess where we're going to look. Let me erase that. Let's look in the data for places where only the hydrogen ion, only the acid concentration changed. Everything else stayed the same. Okay? So, that stays the same. That stays the same. But this doubles. 0.0005 compared to 0.001. This one down here is double. So from here to here, I doubled that while this did not change and this did not change. So I'm factored out the effect of peroxide and the effect of I minus, and I'm just looking at the effect of the hydrogen. Well, let's see what happens. I doubled the acid concentration, right? pH meter should be lower because it's more acidic. I doubled the acid concentration. What did that do to the rate? It did nothing. I got the same exact number. Now remember, in a real experiment, this might be 1.16, right? It's not going to be perfect, okay? But in our data, we tend to make it pretty close, okay? I doubled this, but I got no effect over here. I got exactly the same. The only number that I know of that will do that, I have a doubling over here, but I only got a 1 over here, right? What is Z? Z has got to be to the 0 power, because when something is raised to the 0 power, anything to the 0 would give you 1. So we just proved that holding the peroxide and the I minus constant, when I doubled the hydrogen ion concentration, I had no change in initial rate. That's 0 order. So I figured out the 3 orders for my reaction. It was first order here, and 0 order here. Okay? That's what it looks like. So man, now you're getting a lot of points on the test, right? You're close to done. That was the hard part. Okay, when something is to the 0 power, it doesn't matter. So you can just leave it out. Any number, I don't care if it's 50 gazillion, to the 0 power, just leave it out. So that's why it disappeared here. You're just multiplying by 1. So what is my rate law? The rate for this chemical reaction is the rate constant times the peroxide concentration to the first times the iodide concentration to the first. Since they're first power, you don't have to write the 1. The 1 is understood, right? Nothing means first power. Okay, next, what's the overall order? Second order. 1 plus 1 is 2. So if somebody asks you, what's the overall order? The overall order of this chemical reaction is second order. Okay, now that we know the rate law, we can plug in any one set of data. We've got 4 sets of data. Any one set we can use to get the rate constant. In fact, you could do it for all 4 if you wanted to, and you should get the same number, because rate constant is independent of the concentrations. How fast it occurs is dependent on the concentration, right? The higher the concentration, the faster it reacts. but the rate constant is independent. So I always pick the first one, okay? But you want to be different? Pick the fourth one. Shouldn't matter. In fact, you'll get exactly the same answer for K no matter which set of data you plug in. Just be consistent. Get the whole row and plug it in to your now new rate law, where this is a 1, this is a 1, and this is a 0, so we leave it out. Okay, so here we go. Okay, I rearrange it and I plug in. Okay, I solve it for K. K is equal to the rate divided by the concentration of peroxide, the initial concentration of peroxide, that's what that little 0 means, times the initial concentration of iodine. Okay, I put all my numbers from the first experiment. Go back and you'll see that. There's the first experiment, this and this. This didn't matter, and this. Okay, plug them all in with units. K, the units will work out correctly. If I put them all in, the numerical value I get is 1.15 times 10 to the minus 2. What happens to units? Molarity cancels with this molarity. So I've got 1 molarity in the denominator. That's molarity to the minus 1. And seconds in the denominator. That's seconds to the minus 1. Okay? So you could write it like this. I actually like it like this. Okay? Sometimes you'll see moles to the minus 1, seconds, liters. I prefer the top one. Now that you know the rate constant at this temperature, you can calculate the reaction rate under any conditions and pressures. So once now you know the rate law and the rate constant, okay, someone gives you a different scenario and they say, well, how fast is this going to react? What is the rate? Okay, so here's a different scenario. Same situation, same temperature, right? Because rate constant K is definitely very much a function of temperature. What is the rate of the reaction when the I minus is 10 molar and the peroxide is 10 molar and the hydrogen ion concentration is 0.1? This corresponds to a pH of 1. Okay, wow, man, get out of town. This is a huge concentration of a oxidizer and a peroxide, right? So you're going to have a violent reaction between these two things because these are enormous numbers next to the ones that we had. But let's plug them in and see what happens if I put together 10 molar iodine with 10 molar hydrogen peroxide. Okay, we know the rate is equal to the rate constant times the concentration of peroxide times the concentration of iodine. So at that particular temperature, this is how fast it would react. Just multiply the three numbers. Molarity times molarity to the minus 1 gives you just molarity. And then seconds is still to the minus 1. It didn't cancel with anything. So the rate of this chemical reaction would be 1.15 molarity per second. Wow, that is, you would be chugging through materials. This would be an explosion because it's also an exothermic reaction. If the reaction happened that fast, it would create so much heat, and that heat would create pressure. It would explode out. Heat and pressure in a short amount of time makes something explode. Okay, so what was this last step? Once you know the rate law and the rate constant at that temperature, someone could ask you about a different scenario of concentration and you just plug them into the rate law. Okay, the hard part is determining the rate law. Okay, that's a perfect place to stop. We'll pick up on page 11 in the third video. Thanks.